Okay, Riles. I recognize that we might need a little bit more work with the algebra on lesson 5.9, example D. So first off, I'm going to walk you through the solution that's in the printed notes, and then I'm going to suggest using a couple of different log properties and showing you which log property actually doesn't result in a more efficient solution either. So the example in the printed notes, first thing that I want to show you is that unlike a computer, my handwriting is a little bit ambiguous. So I will be generally surrounding my power for my logarithm in brackets. This will be really important when you start multiplying it. And I probably should have done that even on the printed notes. It's not required when you just have log base 5 of 3 x to the exponent 4. It should be understood that you're not doing x to the exponent 4 times log base 5 of 3. But if it looks like that, then the reader will be confused. Okay, so in the printed notes, I jumped right in to the chain rule. I did the derivative is, let's take the derivative of the top. The derivative of the top is the derivative of a general logarithm function. So that will be the reciprocal of the power. That's 3x to the exponent 4 multiplied by the reciprocal of the natural logarithm of the base. That's the natural logarithm of 5 multiplied by the derivative of the power. The derivative of the power is going to be 12x cubed multiplied by the bottom. That's 5 to the exponent 2x. Notice my choice of using brackets around the base of 5, just to make it clear what's being multiplied here. Minus, let's do the derivative of the bottom. The derivative of the bottom. The bottom is an exponential function. Its derivative will also be an exponential function, but it's going to be a vertical stretch of that exponential function by the natural logarithm of the base. Let's throw a bracket around there. Multiplied by, well, the function's been stretched horizontally, so that's going to affect its rate of change, multiplied by the derivative of the exponent. So it's the derivative of an exponential function is the function itself multiplied by the natural logarithm of the base multiplied by the derivative of the exponent with respect to x. Okay. This needs to be multiplied by the top. And I squeeze it in here? Log base 5 of 3x to the exponent 4. Yeah. All over the bottom squared. Okay. Now, first thing that I did in the printed lesson was just tidy up this numerator a little bit. Let's get dy by dx equals, and you know what? Maybe I'm not in a rush to get rid of the fractions over fractions, since I see there's some simplification that will occur here already. Let's do that simplification. This 12 is divided by that 3. That leaves me with a factor of 4 in the numerator of the numerator. 3 of these powers of x will divide 3 of those powers of x, leaving me with 1 power of x, 1 factor of x in my denominator. I'm going to have the natural logarithm of 5 in the denominator there. I'm going to tidy this up and maybe just put my constants coefficients out front. I'll see a subtraction of 2 times the natural logarithm of 5. 2 ln 5 is my numeric coefficient. And then there is a oh, looks like, sorry, I missed one other thing that I did. Looks like I think this is the reason why I was surprised, because I haven't done this in years, is I decided to divide instead of factor first. It's problematic. It can cause problems for students, but it just saves me so much writing here that I think it might be worth it to divide the 2x factors of 5 from the numerator and from the denominator. And that's why it's not going to show up on this expression here. So I've got 2 ln 5 times log base 5 of 3x to the exponent 4. Sorry, like that. Okay, and that is now all over 5 to the exponent 2x. So what I ended up doing in the printed lesson here, instead of sort of clearing my denominators, I saw an opportunity to actually simplify by separating this, by using the distributive property first and then finding a common denominator. It took me a while to figure out what I had done there. I'm not sure that's how I would do things these days, but it kind of works out in an interesting way here. So what I'm going to do is I'm going to do 4 divided by x ln 5 divided by 5 to the exponent 2x. And this division here is going to be multiplying the reciprocal. It'll end up having another factor of 5 to the exponent 2x in that denominator. This itself might seem a little bit strange. I'm not sure it's an approach I want to advertise. I mean, try out on your own a numeric example of 1/3 divided by 2, and you'll see that that's going to be 1/6. There's going to now be another factor of 2 in the denominator. Over here, what happened? I think nothing on one step. 2 ln 5 log base 5 of 3x to the exponent 4 all over 5 to the exponent 2x. Okay. Now comes the task of finding a common denominator if I want to group these back together again. But I'm not in a rush to multiply both sides by the natural logarithm of 5. So it looks like what I decided to do here is change this general logarithm into a natural logarithm using a change of base. So let's keep this 4 divided by 5 to the exponent 2x. Let's put a bracket there, multiplied by x, multiplied by the natural logarithm of 5, minus 2 ln 5, and then I'm going to use a change of base here. So I'll have the natural logarithm of 3x to the exponent 4 divided by, and then I'll have 5 to the exponent 2x multiplied by the natural logarithm of 5. So I already have a shared denominator factor of natural logarithm of 5. Now this would raise the question, why didn't you use a change of base sooner? And that's a very good question, and I'm going to do that in my second approach. Question about, well, why don't we use some log properties here? Let's just have a quick conversation here and recognize that this is not a power with an exponent of 4. So this expression, natural logarithm of 3x to the exponent 4, does not equal 4 times the natural logarithm of 3x. This is where understanding how your log properties work is very important. You don't just move an exponent out front magically. That's not how that works. What this would be is you could write it as the natural logarithm of 3 plus the natural logarithm of x to the exponent 4 using your product rule first, because this is not a power right now. This is a product. This might remind you of me asking you to use your limit properties one step at a time. And my argument here is that I don't see a power, which then could be written as the natural logarithm of 3 plus 4 times the natural logarithm of x. Well, that ends up just having a sum that would have to be distributed through here. So I might show you this approach on a second or a third attempt at this derivative, but it generally doesn't really yield that many great returns when you have a more complicated expression to the left here. To tidy this up then, I will find a common denominator by multiplying by 1 in the format of x over x. And I get dy by dx equals, where is my line? 4 minus, I'm going to put the x next to the 2 times x times the natural logarithm of 5 multiplied by the natural logarithm of 3x to the exponent 4, all over, how did I write the denominator? I guess I wrote it 5 to the exponent 2x, although I'm going to put in more brackets, times x multiplied by the natural logarithm of 5. Now you might be concerned here and say, how am I supposed to know to what level I'm supposed to simplify? And that's a really good question. Usually this is more of the teacher's job to see that the simplification that the student chose to do actually gives an equivalent function. Like with some of our more complicated derivative questions in Unit 2, you might just be asked to find dy by dx when x equals, I don't know, like 1 or some value that would exist. You might, once in a while, I've actually given the students the target. I've told them, show that the derivative equals this, but that causes a lot of problems for the OCD students. because they will not stop a question until they get this answer, no matter how many mistakes it takes. This is a relatively complicated expression here. I'm not sure that that it's something that I would want to mark, but you're responsible for these rules. Let's take another run through this question though and see how we can simplify it. Okay, so right back to the start. Let's look at the function. Y equals, nope, sorry, cat on the keyboard. Oh dear. Okay, y equals log base 5 of 3x to the exponent 4 divided by 5 to the exponent 2x. So yeah, I think you should know your derivatives of general logarithms, but I have seen students that just always choose to use a change of base instead. And there's some big advantages here because I'm going to use a change of base, and I'm going to write this as the natural logarithm of 3x to the exponent 4 divided by 5 to the exponent 2x multiplied by the natural logarithm of 5. And it might just look like I've kind of changed my quotient rule around a little bit, but I do have a much simpler numerator. And the argument I'm going to make now is that this right here is a constant multiple. The other option from here, if you wanted to continue, I'm going to say you could use these properties up here. And I might leave it up to you to see that they don't really pay off. So you could go natural logarithm of 3 plus the natural logarithm of x to the exponent 4 all over 5 to the exponent 2x. Let me deal with this constant multiple first, get that out of there. And then write this as the reciprocal of the natural logarithm of 5 multiplied by the natural logarithm of 3 plus 4 times the natural logarithm of x all over 5 to the exponent 2x. Let's just take a look here. We have a chain rule that will have some common factors that we'll need to simplify. Is exchanging that for a sum rule? Well, if we didn't have a denominator, then sure, taking the derivative of a sum is going to be much easier. But with the quotient rule, that means that I'm going to have a bracket of a bracket that has a factor of ln 3 plus 4 ln x inside it that would need to be distributed anyways. So it turns out not to be that beneficial. If you accidentally do that, it's not going to ruin your question. Your question might be a little bit more complicated, should still receive full marks. Let's see. Let's just tidy this up to the format from which I will be taking the derivative. And that is a constant multiple of the natural logarithm of 3x to the exponent 4 divided by 5 to the exponent 2x. So still using a quotient rule, but I've got a common factor out of the way, and I don't have any general logarithms to deal with. dy by dx is going to be a constant multiple of, let's do the derivative of the top. The derivative of the natural logarithm of a power with respect to the power is the reciprocal of that power. Then I need to multiply by the derivative of that power. The derivative of that power with respect to x is 12x cubed. I might try to maybe write this up in the numerator next time I see a function like this, but I don't know. I'm going to be tidying up anyways. So that's the derivative of the top times the bottom. Maybe a bracket would be useful there. Minus, let's do the derivative of the bottom. Derivative of the bottom, derivative of an exponential function is an exponential function multiplied by the natural logarithm of its base multiplied by the derivative of its exponent. Okay, this is the derivative of 5 to the exponent 2x with respect to 2x multiplied by the derivative of 2x with respect to x. That's the derivative of the bottom multiplied by the top. All over the bottom squared. These exponential derivatives I've kind of mentioned, kind of like some of the trig derivatives that we've seen. When the derivatives are so simple, or when the derivatives start to look like the function itself, quotient rules can become more challenging. It can be hard to see that this right here is the bottom and this right here is a part of the derivative of the bottom. Okay, this right here is the top and this right here is a part of the derivative of the top. So just take your quotient rules slowly. All right, let's start tidying up. I'm just going to sneak that factor of the natural logarithm of 5 down into the denominator here. So I'll have a ln 5 in the denominator. Same argument here, even though they can cause problems, I'm going to distribute this division. I'm going to divide both terms in my numerator by 5 to the exponent 2x, and I'm going to divide my denominator by 5 to the exponent 2x. 5 to the exponent 2x. Over here, let's simplify 12x cubed divided by 3x to the exponent 4. That will be 4 divided by x. Over here, let's just rearrange to minus 2 ln 5 times natural logarithm of 3x to the exponent 4. Okay. And now we're one step away of just multiplying the numerator and denominator by x. Since I shouldn't have fractions in fractions, I get 4 minus 2x ln 5 ln 3x to the exponent 4 all over x ln 5 times 5 to the exponent 2x. I'm being inconsistent with the way that I'm writing my brackets, sort of on purpose to show you that there are many different ways of writing the same expression. Okay. It is a heavy question. It is definitely challenging. Try more than one approach, because I think you can convince yourself that usually using log properties is a good idea, but not always, if it means you're going to have more distribution. The same argument could be made right here. Like, am I done? Shouldn't I use this log property? Well, why? Like, what's my purpose? I would just have to distribute through ln 3 ln 3 plus 4 ln x. It's not going to have like terms show up. It's not going to cause any factors to divide out. So why are you doing it?